All right. Well, thank you for taking the time to be with us today. I see a few faces out there I recognize. A couple. I am David Flynn, the CEO of Hammerspace. You might know me. My claim to fame is I founded the company Fusion.io and introduced the what became NVMe in the industry. But here I'm talking more about the software side of things, and excited to talk about some developments in the world of standards-based, high-performance file systems, which was all about being able to exploit that crazy performance that you can now get from NVMe. And I'm joined today on stage with Gary Grider, who was one of the motive forces behind getting this work started a good 20 years ago at this point. So since we're going to be talking about the culmination of a lot of work that went into building this stuff, I think it'd be great to kind of start with Gary, talking about those things, and then I'll jump into some of what's going on now. So let me turn the time over to Gary. Oh, I didn't even introduce who he is, so my apologies. Gary is, what is the technical? He's the division leader of Los Alamos National Lab. So I liked how he put it earlier this morning in another setting. He's the guy responsible for things like Lustre and GPFS and others, Ceph from that work. So, call it Godfather of the HPC world, which has now gotten really sexy with AI since everybody wants crazy performance. So, Gary, here you go.
Thank you, David. I don't have a whole lot to say. I just wanted to set up the stage for David to talk more in depth about PNFS and Hammerspace and where all that is. But I'll talk a little bit about where it came from and why it's kind of interesting, at least incredibly interesting to me. So there's a number of different kinds of storage use cases that all sites have. Some sites have more than others. Our site has home and project space and SMB space and things like that for the normal NFS kind of access. It also has this thing called read mostly. Our version of read mostly storms is where you fire up 1 million cores all at once, and it happens to be a Python script or set of Python scripts. And the first thing in Python is include, and there's 400 includes, and then every one of those damn include files has 400 more includes, and so there's 2,000 or 3,000 file opens that happens from every million core that you have just launched, and that's the definition of a read storm for us. And so how do you service a need like that, right? So there's other people that have all kinds of read storms. I think AI training has read storms as well, but ours is a super highly synchronized read storm. Data analytics, so at our site, you write out a petabyte every time you do a checkpoint of those 1 million cores, and you do 10,000 time steps, you got 10 exabytes. What do you do with it? Do you ever want to query that? Well, the only way to query it would be to read it all back in, and that would be pretty ugly. And you'd require a petabyte-size supercomputer to be able to just read the data in and look through it, so it's not really very practical. So push-down analytics, it didn't come from the HPC community. It kind of came more from the data analytics community, but we're super interested in that because the data gravity is so large at our site. Distance, so most places, most sites have more than one site, and so you have to worry about being able to do file sharing and information sharing across sites in reasonable ways, and there's been solutions to that in the past. Archive, so not everybody can keep all their data on flash. I know we can't. You have to have some number of exabytes of something slower and cheaper, and so we do, and it's important to include that into the namespaces and things like that so that you can find things. Massive scale, we have two kinds of scale out problems besides that read storm that I talked about. One is everybody, all million cores, write to the same file at once. So everybody does an open of the same file and then writes in different places. And it's kind of worse than that because all of them write all their pressures together in the first part of the file, and then they all move down, and then they all write into their temperatures into the file, and then they all move down, and they all write into the, whatever the next variable is, and there may be 100 of these, and that makes up a petabyte across the memories of those million cores. And so what that really means is a million cores are bearing down on one little piece of the file, and then they're bearing down on the next little piece of the file, and so a normal file system would fall over. This is the reason Lustre exists, by the way. It's what it's there for. And so anyway, that's one scale. And the other scale is a million cores each write their own file. Well, that's fun. A million cores all decide they want to do an open with create in the same directory. What happens? Well, the metadata server falls over because it's hard for that, hard to handle that kind of workload. And so those are our two scale-out workloads, and then a course object or cloud or that kind of thing, so people have a need for that kind of access. So anyway, there's all these things, and a long time ago, back 2002, we started this project with University of Michigan City, and that was to essentially start to explore how to do PNFS. And where did PNFS came from? Well, it came from us building things like Lustre, which we did, and building things like Ceph, which we did. We paid University of California, Santa Cruz to do some of that work, and early on. And our problem was we didn't want to have to create a parallel file system client for every parallel file system we built, because at the time, getting clients into Linux is hard. Getting stuff into Linux is still hard. It's easier than it used to be, but getting file system clients in was pretty hard. And so we had this idea, we'll make a parallel file system NFS client and get it distributed with the Linux distro, and that way the client can always be the same, and then the people can innovate on the server side. It was a good idea. It took a long, long time to get that standardized. It took a long time to get it right. There was a bunch of underbelly that had to be built to make it work. Things like compound RPCs, where you lump a bunch of RPCs together before you send it to the server, so you save round trips, and things like you had to have a mapped because you were going to parallelize the file, so you had to have a parallel map of the file. You need to make that map recallable, and recallable implies statefulness, and NFS wasn't stateful at the time. And so we paid for 8 years or so of just work to try to get the underbelly inside of it, of the NFS, in kernel NFS, to make all these things work. And so some of the work was that David mentioned was that. So the message I really wanted to say was, until recently, very recently, I wouldn't have thought that all those workloads that are pretty different could all be handled by one file system technology. Not necessarily the same file system, although it could be, but at least just one file system technology. And why would I think that that's hard? Because I've been trying to do that for the last 40 years. And furthermore, I think it's interesting that an open, things that ship with Linux, open distro kind of software, is enabling all this, which is really pretty remarkable. And I wouldn't have thought that was possible, but it's really important, because if I have to have 4 or 5 of those different things today, I have to have 4 or 5 different kinds of file system technologies to do those things. And if I don't have to do that anymore, it gets a lot better for me. And so I've been surprised how far PNFS has come since the early days when we paid to have the early work done. And it's super impressive to see how fast it's come on. And I have to credit AI a little bit for that. AI has pushed HPC out to the common person, so they need a more standardized solution and less customized, like Lustre and the like. So anyway, to talk more about the solution that's available for this is David's going to.
Thanks, Gary. So that kind of sets the stage that what we're talking about here is something that's standards-based, built into Linux, and able to address the full dynamic range that has required literally more than half a dozen different file systems in the past that could now be done within one. And this goes to the context today. performance is no longer a niche. It's now a mainstream thing. Thanks to AI workloads, everybody needs performance. And it's not just about the last mile delivery of the data into the GPUs from nearby storage, it's also about the long haul logistics of getting data across data centers and getting data across storage systems into the right system that can then feed that last mile. And the interesting thing is, this can all be done within the same file system so that the data movement is done transparently, and that's what we talk about as data orchestration. It's not a fancy new name for data management. It's where the data movement is happening from within the file system across whole data centers and across separate storage systems of different types from different vendors, but all in the same namespace. So what has really made this possible is the fact that Linux is ubiquitous, so you only have to worry about one client. It's consolidated the landscape. So NFS 4.2, what I did when I left Fusion IO is I went and recruited the Linux kernel maintainer of the NFS stack, Trond Mikkelbust. He's our CTO. And we took the early work that had been done with parallel NFS and we patched it up because it had been a design by committee with existing storage vendors whose file systems weren't parallel file systems, so they had conflicted interests, and it was a design by committee thing. And they were still worried about half a dozen different operating systems. So what has changed is that performance is a mainstream need, Linux consolidated the OS landscape, and the groundwork was laid, but now it wasn't a design by committee thing. We could take and fix the final pieces, have them fall into place, and build a true world-class parallel file system that can address the full range of workloads all within one file system, including what has traditionally been data management, the movement of data across the world. So when you look at the evolution of file systems, we've had these HPC file systems, we've had traditional NAS, and those two camps have been very separate. On the one hand, you have issues with scaling performance, and on the other hand, you have issues with scaling the manpower, because not everybody can afford the kind of talent that it takes to run a science project and build these HPC file systems. So what you need is something that is standards-based, built in, and yet gets to the performance level of not just HPC file systems, but for the different use cases. Massive ingest, writing all to one file, writing millions of files. Basically, it needs to be good at all of these different workloads. So I'll use for an example here, and Meta has been kind enough to talk about this publicly. They have used Hammerspace for training of Llama. And the beauty is, because it's standard-based, they didn't have to load any special software on their GPU nodes. It's just off-the-shelf Linux. But moreover, they didn't have to load anything special on the storage nodes. It's just virgin off-the-shelf Linux. No proprietary software was necessary on either the clients or the storage nodes. Hammerspace, which is the metadata control plane, are those three nodes in the middle at the bottom that we call the Anvil nodes. That's what has all the file system metadata and is the control plane. So it's a true parallel file system in that the control plane never touches data and it never gets involved in the I/O path, which is what allows for that crazy scalability. So it's a very simple concept. Split the control plane from the data plane. It's the same thing that allowed software-defined networking to scale. That's the fundamental architectural innovation of a parallel file system. We took that and said, let's make it so anything that speaks old NFS can actually be a storage node in a parallel new NFS world. And that's what has allowed for this unlocking of performance. So if we look at the roadmap, since we only have a few minutes, this is interesting stuff that's going on. We, let's see, I don't need all that. Parallel NFS was introduced a good, a couple of decades ago initially, that implementation. Hammerspace introduced the flex files layout, because one of the other problems with the original standard is it wasn't a single standard, it was a family that allowed every different vendor to have their own layout, and that just might as well be no standard at all when every vendor has their own. So what we did is said, look, let's just make it so it's NFS 4.2 that stacks on top of NFS 3. So now anything that's NFS 3 is a storage node, including Virgin Linux, which is what, for example, Meta was doing. And so that flex files layout we introduced a good 5 or 6 years ago. It's now built into every modern Linux. Anything from RHEL 7 forward already has everything that's needed in it. Now, some of the new stuff going in is being able to put NFS over TLS and having the parallel NFS hand out all the certificates and stuff to secure the communication to all of the storage nodes. SecGSS and all of the mess that gets involved there with Kerberos and everything, too big of a pain. Being able to just put NFS on TLS allows you to secure data in flight. Of course, you can secure it at rest with hardware or software encryption on the node. The other important thing that's going in now, and thanks to the collaboration with Gary and Los Alamos, is the ability to have many writers to a single file, even when there's a lot of overlap in the same area. So they're not, neatly separated on different sectors. It's like all potentially million nodes are hitting the same region of the file at once in sequence. That has to work fast. So there's innovations going in now around N-to-1, as well as distributed erasure coding, so that the client can write diffuse across many storage nodes. So it's a combination of striping and erasure coding that would allow clients to write across potentially thousands of separate storage nodes to be able to get the aggregate performance of all of them. And then this is something, I should have put it in the reverse order. Oh, that's we talked about the erasure coding. And the last one is, it's called local I/O, and this just went upstream into Linux in this last merge window. What this means is that when the NFS client on Linux connects to an NFS server, it has a little sideband chat to say, are you me? Are you the same kernel? Are you on the same physical host? And if it is on the same physical host, then it bypasses the entire NFS stuff and goes directly across the kernel, passing memory buffers by pointer. Net result is you get the full performance of local NVMe, even though what you've attached to is a shared file system. This has major implications for how containers talk to each other, and for a parallel NFS world where data can be orchestrated. It means that Hammerspace can position the data files to be on the same nodes that are using them, and the system will auto-detect that, bypass all of the overhead. So these are some of the new things going in recently. And with that, I'll go ahead and wrap up because we're out of time, and that's a good place to stop. Thank you.